Okay, let's go on to the next topic today, adsorption isotherms. इससे पहले वाले लेक्चर में हमने क्या किया था? We had done chemisorption. Okay, we did physical adsorption. Then we did the differences between the two, and the last topic which we did was activation of adsorption. That is, how can we increase the extent of adsorption? Today we are going to do adsorption isotherms. What do we understand by isotherms? Basically, adsorption isotherms, or when we are talking of only isotherms is the process at constant temperature. ठीक है? So यहाँ पे adsorption isotherms का मतलब क्या हुआ? It is a graph which gives us a relation between extent of adsorption and pressure at constant temperature, right? So it is the graph which is giving us a relation between extent of adsorption. Extent of adsorption, I had told you that it is related upon, or it is given as x upon m, where x is the amount of adsorbate absorbing upon per unit area of the adsorbent. That is what extent of adsorption is. Okay, so between extent of adsorption and pressure, and we are keeping the temperature constant. The first relation that was given by a scientist whose name was Friedrich in the year 1909. Okay, and these adsorption isotherms or curves or graphs, they are given the name after the name of the scientist, and they are known as Friedrich adsorption isotherm. In this case, we see that we are looking, whenever we are looking at a graph between x upon m and pressure at constant temperature, the graph at various temperatures was plotted. At 0 degree centigrade, the graph came to us like this, right? And at minus 29 degree centigrade, the graph was plotted in a similar manner. And when we were further decreasing the temperature to minus 78 degrees Celsius, even then the graph was plotted in a similar manner. Okay. So we are visualizing the graph. Let's say we are visualizing the graph at minus 78 degrees Celsius. Over here we are categorizing, or we are dividing the graph at various pressure ranges. Okay. So यहाँ पे हमने ये वाला ले लिया. This is the range at low pressure. So when we are talking about the range of the graph at low pressure, you can see over here that the graph is almost coming as a straight line. Okay, so at low pressure the expression given was that x upon m, that is directly proportional to pressure. ठीक है? Or we say that x upon m, that is equal to Kp, right? When we are looking at high pressure, let's say this is the curve at high pressure. So you can see that it is almost coming as a straight line. Then second, at high pressure, we say that extent of adsorption, that is directly proportional to p raised to power 0, which expresses that extent of adsorption is independent of pressure. ठीक है? Or we can say that x upon m, that is equal to k dash p naught, where k dash is the constant of proportionality, right? The best expression, or the most favorable expression given by Friedrich, was at intermediate pressure. So when we are looking at the expression at intermediate pressure, the expression that was related as x upon m is directly proportional to p raised to power 1 by n. Okay, where n was any integer, right? Where n was any integer, and the value of n that was anything between 0 to 1. Right? The value of n was anything between 0 to 1. So now this expression becomes x upon n, that is equal to Kp1 by n. This expression at intermediate pressure that explain the French adsorption to best of extents. Okay? So now if we are applying log on both sides, if we are applying log on both sides, what will we get? We will get log of x upon m, that is equal to log of k, okay, plus 1 by n log of p. This is the expression which we give for French adsorption isotherm. Okay. Now when we are looking at the validity of this law, for the validity of the law, we plot a graph between log of x upon m and log of p, and the graph that comes as a straight line. Okay? If we are extrapolating the graph till here, then the intercept of the curve that gives us the value of log of k, intercept of the curve that is going to give us the value of log of k, and the slope of the curve that is given by 1 upon n. Okay? Slope of the curve that is given by 1 upon n. When we calculate the slope of the curve by taking this value as theta and the slope come to as a straight line, it confirms or it validates the law of French. Okay? Otherwise it does not. Is it clear? Now we have 2 or 3 ranges over here. Let's say if we are saying that the value of 1 upon n that comes equal to 0. We are calculating the value of 1 upon n from the slope. If the value of 1 upon n that becomes 0, then remember that x upon m that is going to be constants. Okay? Then the extent of adsorption that is going to be constant, and if the extent of adsorption is constant, it means it is not depending upon pressure, or we can say that at 1 upon n is equal to 0, the extent of adsorption is independent of pressure. Okay? So if in the question it is given to you that what happens to the extent of adsorption if the value of 1 upon n that is equal to 0, then you have to mark the option which says that x upon m is independent of pressure. See? Then second what we have over here is if the value of 1 upon n, because we are saying that the value of 1 upon n can vary from anything from 0 to 1. Okay? And if the value of 1 upon n that becomes equal to 1. Okay? In that case, what will we have? That x upon m that will be directly proportional to pressure. Okay? So we say that in that case, the extent of adsorption that is going to be directly proportional to pressure, or with increase in pressure, the extent of adsorption that will increase. Okay? So this is what the French adsorption isotherm is. Now what are the drawbacks of this graph which we have done over here? What are the drawbacks of French adsorption isotherm? Number 1, the first drawback is that the French adsorption isotherm that is purely empirical, right? Which means that it will have a totally numeric value, does not give us any theoretical concept about it. ठीक है? Then second is it does not consider the role of surface area. It does not consider the role of surface area, because when we were looking at the factors on which the extent of adsorption was depending, in that surface area had a big role to play. That is the reason why we were activating the charcoal to increase the surface area, or we were trying to break the pieces, finely divided metals we were taking, that was also to increase the surface area. But French adsorption isotherm is not taking into consideration the effect of surface area on extent of adsorption. So that was another drawback. The third was it could not explain the extent of adsorption at high pressures. It could not explain the extent of adsorption at high pressures. So it is, and also number 4, it is only applicable to physical adsorption. It is only applicable to physical adsorption. ठीक है? Clear हो गया? Why only to physical adsorption? Because it considers multi-molecular layer adsorption. Okay, and physical adsorption is multimolecular. Got it? Now to explain all these flaws, there was another scientist who gave us another adsorption isotherms which are known as Langmuir. After the name of the scientist, they are known as Langmuir adsorption isotherms. Right? So you can just write down the postulates of this. What did he propose for his adsorption isotherm? The first one was that gases form unimolecular layer. Gases form unimolecular layer on the surface of adsorbate. Unimolecular layer on the surface of adsorbate. Number 2, gases undergoing adsorption. Gases undergoing adsorption behave ideally. Undergoing adsorption, they behave ideally. ठीक है? Then number 3, adsorption of a gas molecule. Adsorption of a gas molecule is independent of the surrounding molecules. Independent of the surrounding molecules. ठीक है? Which means that whichever molecules they are getting adsorbed on the surface, it does not depend upon the fact कि जो surrounding molecules है whether they are undergoing adsorption or not. Right? So each molecule has its own role to play for the adsorption to occur. Right? And number 4, dynamic equilibrium that is going to exist during adsorption. How dynamic equilibrium? We are saying that there are 2 processes which are taking place during adsorption. The first one is adsorption on the surface or adsorption of adsorbate on the adsorbent. ठीक है? Adsorption on the surface and simultaneously desorption. ठीक है? Simultaneously desorption. Now dynamic equilibrium means that when we are talking of both undergoing over here. In that case, we will have extent of adsorption, or we can say the forward reaction, that is going to be rate of adsorption, okay? And the backward reaction, that is going to be rate of desorption. So at equilibrium, rate of desorption, okay? So at equilibrium, what is going to happen? Rate of adsorption, that will become equal to rate of desorption. Now to look at the reaction, it will be felt that there is no reaction taking place. So the dynamic equilibrium means that the process is always moving during equilibrium. Rate of forward reaction will become equal to rate of backward reaction, or rate of adsorption, that will become equal to rate of desorption. Mathematically, if we are trying to explain the Lanier adsorption isotherm, then mathematically we can give an expression, that is x upon m, that is equal to k dash p upon 1 plus kp, where k and k dash, they are going to be constants. So over here we are going to discuss two cases now. So let's discuss two cases. Case 1 is when pressure is very high. Because we just studied that Freundlich adsorption isotherm failed at high pressures. So Lanier gave us an expression for high pressure also. It is said that when pressure is very high, in that case 1 plus Kp, that becomes equal to Kp. Okay, 1 plus Kp, that becomes equal to Kp. So according to that expression, x upon m over here will become equal to k dash p upon Kp, because 1 plus Kp, that is equal to Kp. Okay? And at high pressure, the degree of adsorption is going to approach a limiting value. Why? Because 1 plus Kp, that becomes equal to Kp. So if we are trying to extend the curve, this is the limiting value. Got it? Second is case 2, when pressure is low. When pressure is low, in that case 1 plus Kp approximately becomes equal to 1. So if 1 plus Kp is equal to 1 over here in that equation, x upon m, that will become equal to k dash p. Right? So at low pressures, the extent of adsorption is directly proportional to pressure, because k dash over here is a constant. So we can say that x upon m is directly proportional to p. Right? Whereas at high pressures, x upon m, that reaches a limiting value. That reaches a limiting value, right? Then adsorption from solution phase. If this, what we are doing over here is, we are taking into consideration the gas phase. That is why we are considering pressure. In case we are taking the solution phase, for example, if you've kept a solid in some solvent, right? Let's say you've kept charcoal in some liquids. What will happen, for example, if you keep charcoal in cane sugar, then what will happen? It will absorb all the color of the cane sugar, and the concentration of the solution, that is going to dip down. That means that adsorption is also, it can be, or adsorption is also taking place in the solution phase. Okay, in case adsorption that is taking place in the solution phase, then extent of adsorption xm can be given as kc raised to power 1 by n, where c, that is the concentration of the solution. Applying log on both sides, what will we get? Log of x by m, that is equal to log of k plus 1 by m log of c. Okay? Then the next we have, these were the isotherms. The next we have adsorption isobars. Adsorption isobars. Adsorption isobars, they give us a relationship between extent of adsorption and temperature at constant pressure. Constant pressure. It can be seen that adsorption isobars, they give us different graphical representation for both physical and chemical absorption. Okay? So we are plotting a graph for physical absorption between x by m and temperature at constant pressure. The graph comes like this. That is, with increase in temperature, the extent of adsorption keeps on decreasing. This is the graph for physical absorption. Okay? And if you are doing it for chemical absorption, then x by m and t, the extent of adsorption first increases and then decreases. So you can see over here that this is the graph for physical absorption and this is the graph for chemical absorption. Okay? So both these graphs, they can be correlated to the differences in physical absorption and chemical absorption. Right? Now why the difference over here? Over here in chemical absorption, we know that formation of chemical bonds have to take place. So initially when the adsorbate that is trying to adsorb on the surface of the adsorbate, we need high temperature for the bonds to be formed. Okay? So when we keep on increasing the temperature, the extent of adsorption keeps on increasing. Once the bonds are formed, after that if we increase the temperature, the bonds they start breaking and a reverse process will happen, that is desorption is going to take place. Therefore, the extent of adsorption that keeps on decreasing. ठीक है? फिर उसके बाद next हमारे पास क्या आ जाता है? That is adsorption isotherms. The third which we are going to discuss over here, that is adsorption isotherms. What are adsorption isotherms? When temperature increases, we are saying that degree of adsorption, we have just studied that degree of adsorption depends upon two factors. One is temperature and the other one which is pressure. So at constant pressure, we discuss the isobars and at constant temperature, we discuss the isotherms. Now when temperature increases, what happens to extent of adsorption? That is going to decrease. And when pressure increases, then extent of adsorption that is going to increase. Okay? Now plot of temperature versus pressure. If we are plotting a graph between temperature and pressure for a given amount, okay, for a given amount, that is, we are keeping the amount of the substance or adsorbate constant over here, then that is known as what? Adsorption isotherm. That is known as adsorption isotherm, right? So we've done what adsorption process is to quite a detail. Let's go on to the applications of adsorption. There are various applications of adsorption. Like for example, we can use adsorption in the production of high vacuum. What is done in this process in order to, for example, we are taking charcoal, okay, and charcoal that is cooled in liquid air, okay, and then we connect it to a vessel which is already empty. Now what is the purpose of keeping this charcoal is that this charcoal will absorb all the remaining air which is there in the vessel, as a result of which it is going to create a high vacuum. Okay, we have already taken a container which we have evacuated totally and it is connected to a piece of charcoal. Now charcoal has a property to absorb certain gases. Okay, so this piece of charcoal, it is going to absorb the remaining traces of air, as a result of which it produces vacuum in the beaker. Okay, why vacuum? Because there are many reactions which are taking place in vacuum. So that is why to produce anything which high vacuum, adsorption is involved. Okay? Then second is gas masks. This I have already told you. All the miners, coal miners which are working under the earth's crust, there are many poisonous gases which are present. There are gas masks which are formed again of charcoal only. Now this charcoal has a tendency to absorb the poisonous gases, as a result of which the poisonous gases do not enter into the body of the coal miners and they remain safe. Right? So gas mask is another distinct application. Then third is humidity control. Humidity control may we use either silica gel or we also use alumina gel. Both these, they have a tendency to absorb water, as a result of which the humidity of the rooms in which you are staying, that can be decreased by using both of these, right? Then fourth is removing of coloring matter from solutions. Removal of coloring matter from solutions. Now, sugar we know that is formed from sugar cane, okay? But the sugar crystals which we eat or which is available in the market, that is white in color, okay? Otherwise, the sugar cane that has, it's a yellow syrup from which sugar is crystallized. In order to remove the yellow color of the sugar cane, there is a piece of animal charcoal which is placed, and this animal charcoal has a tendency to absorb all the color from the sugar cane, right? So that is used for removal of coloring matter, okay? Then we will study in our next topic. Adsorption is a very important process in heterogeneous catalysis, right? Heterogeneous catalysis. ठीक है? फिर उसके बाद it is also used for separation of inert gases. Inert gases are gases which have no reactivity, like helium, neon, argon, all these, they are inert gases. These inert gases, they absorb at different degrees, right? So depending upon the degree of adsorption of the inert gases, they can be easily separated, right? Now apart from these, there are numerable applications of adsorption. Like for example, there are a lot of medicines in which we can say the process of adsorption that is there, that we will do in detail when we do chemistry in everyday life, right? And then it is also used, the cleansing agent, as a cleansing agent, or we can say that cleansing action of soap, that is also an adsorption process. Okay, then froth flotation process, which is used to concentrate the ores, sulfide ores. Froth flotation, that also we will study in chapter 6. Then we have chromatographic analysis, right? That also we will study in detail, and we had just done kinetics. In kinetics also, when we are doing the catalyst, the surface of the catalyst, they absorb all the reactants so that the rate of reaction can be increased. Okay, so with this we finish our topic for today. Tomorrow in the next lecture we are going to start catalysis.